Hello, my name is Alexander Scheffler and this is joint work with my advisor Steffen Bondorf. We are both from the Ruhr University Bochum in Germany. The title of our paper is Network Calculus for Bounding Delays and Feed-Forward Networks of FIFO Queuing Systems. Now I will give an overview about my talk. First I will discuss the motivation behind deterministic network calculus, or short DNC, as well as its basic definitions and results. Next, I will discuss the objective and our approach. There are many subtleties when analyzing a feed-forward network. Bounding the arrivals of flows within the network is at the core of our paper. Then I continue with the tandem analysis on which the overall procedure relies on. Finally, I will discuss our numerical results. DNC is a theory of deterministic queuing behavior that is able to derive worst-case bounds such as end-to-end delay of a data flow and backlog in a server's queue. Its general challenge is to derive bounds that are close to the realistic worst case. It has been successfully applied to many areas, for example, in the cyber-physical domain, such as airplanes. Moreover, it can be used to rank different network topologies and configurations. Next, we see the overall model. The arrival and departure process of data streams, flows, are bounded by curves, so-called arrival and service curves. These curves model the processes in interval time. Note that the service curve definition takes into account the arrival process and the operator is called convolution. Given these curves, one can compute the delay bound, for example, which is simply the horizontal deviation between arrival and service curves, as we can see in the figure below, with the blue line. However, we have only shown one server and one flow. That's why network calculus provides more results in order to compute bounds of larger scenarios. Most notably is the concatenation theorem. With this, two or more servers can be described with only one curve. In a FIFO queuing system, flows competing for the service multiplex in FIFO order in the service queue and are then served in this order. To separate flows from each other in the analysis, the so-called leftover service curve is important. It describes how much service is left for a flow after taking into account the other flow. For FIFO, one has to set a certain value theta. How to set this value such that the overall bounds get minimized is a challenging problem, because all these values depend on each other. Our paper focuses on the setting in order to deliver a scalable FIFO-aware analysis for feed-forward networks and its tool support. The challenge that we tackle in this paper is to adapt a backtracking scheme to derive arrival bounds to the FIFO analysis, where there are certain peculiarities to consider to derive best possible bounds. We have implemented our approach into the open source deterministic network calculator tool, which is available on GitHub. Our approach combines a previously published backtracking scheme for arrival bounding in a feed-forward network and a so-called least upper delay bound, which has been presented only for tandem topology so far. We coin our novel approach LODBFF, indicating the focus on feed-forward networks. Now I will briefly discuss the arrival bounding procedure. Assume one wants to compute the leftover service for the flow of interest that crosses S1 and S2. Since other crossflows go through S2, namely F1 and F2, we have to compute arrival bounds for these at server S2. For this, we backtrack these two flows to the first server where these two flows diverge, namely S4. After recursively getting the arrival bounds at S4, we will do a tandem analysis on the tandem S4, S3, and based on the leftover service curve, we can compute an output bound for these two flows, which will be then a valid arrival bound for these two flows at server S2. All this indicates that many, but rather short tandems have to be analyzed during this backtracking procedure. When it comes to tandems and LUDB, we have to differentiate two main classes, nested tandems and non-nested ones. A tandem has nested interference if for every pair of flows, either both flows do not have common servers or the path of one flow is included in the other flow's path. In the above network, we have a nested tandem and in the one below, a non-nested one. since F1 and F2 have server 2 in common, but F1 is not included in F2 and vice versa. Note that all the tandem examples here in this presentation are only for simplicity of presentation. The properties and scenarios that are already visible in them will occur more often in complex feed-forward networks, as the combination of tandem analysis is inevitable. The benefit of nested tandems is that one can clearly apply the convolution theorem and leftover theorem in a way to convolve as much as possible, which is called pale multiplexing only once. The LUDB methodology for nested tandems follows this approach and is able to optimize these theta values to get a minimal delay bound on these topologies. However, it is restricted to specific curve types, namely token bucket and rate latency curves. The problem of minimizing the delay bound is formulated as a piecewise linear problem, which can be split into several linear programs. The solution is the minimal objective value of the LPs and is called LUDB. In large feed-forward networks, things get more complicated, why it's crucial to also optimize for output bounding. Since some of the tandems we have to analyze in a feed-forward context will be nested, and with the aim of output bounding, the following lemma is very useful. In short, it states that in order to arrive at a minimal output bound for a nested tandem, one has to solve the LUDB for subproblems of it. On the right, a subproblem would be the subtandem S1 with only flow F1, so without the flow of interest, and the other subproblem would be the subtandem consisting of S2 and S3 with only the crossflows F1' and F2. After calculating both delay bounds with LUDB, one can then compute a fairly good output bound. For our modular tool, we first have to transform this result into the respective curve. As already mentioned, during the backtracking we have to solve several tandems where, apart from the differentiation of nested and non-nested ones, we also consider if the current goal is either output or delay bound minimal. In short, if we start the overall analysis for a flow of interest, then the goal is first delay bound minimal, and for the intersecting crossflows, we start the recursive arrival bounding scheme for which the goal is output minimal respectively. The case of nested tandems works as discussed before. Note that we can aggregate crossflows that share the same tandem path with the flows of interest. This saves us 1 theta in the LUDB optimization problem and makes our algorithm faster. For non-nested tandems, we cut crossflows as the literature suggests. For this, we have a look at the left tandem down below. We can cut before server 2, for which we get the nested tandem on the right. An alternative would be to cut before the last server. In general, all of these cut sets have to be tried out to get the best bounds. With our work, we also want to contribute a new finding when it comes to cutting of crossflows. In case crossflows share the same path as the flows of interest on the current tandem, we suggest to aggregate them with the flows first before subtracting, so these crossflows would then not get cut on the respective locations, which further improves the overall bounds. To our best of our knowledge, this has not been identified before. For the evaluation, we have used networks following the general linear preference model that mimic internet topologies. They were used to evaluate the backtracking scheme that we took as motivation for this work, so we can easily benchmark those results. Thus, we can show how much tightness is lost when the FIFO property that complicates things is not factored into the analysis. Note that we have adapted the arrival and surface curves to allow for different utilization benchmarks. In total, we have 4 network sizes, 20, 40, 100 and 200 devices, and we set the server utilizations to 70%, 90% and 99%, yielding to 12 networks in total. As metrics, we use relative delay bound. For example here, relative to the so-called SFA FIFO analysis that does not convolve tandems like all the other analyses do. On the x-axis we have this relative delay bound. A negative value indicates delay bounds with the respective analysis which delivers better results than SFA FIFO. On the y-axis we have the CDF. Note that Deborah integration acts as a simple competitor for feed-forward networks, because there is the Deborah tool that implements LUDB, however only for tandems. We have combined the Deborah tool with the output bound from the delay theorem, since Deborah only provides the delay bound from which it is not possible to allow for a sophisticated arrival bounding procedure, such as our analysis LUDB-FF. Note that the output bound from delay is an upper bound on the deconvolution-based output bound, and because of this simple procedure, the stability constraint may be violated, yielding to infinite bounds. We can already observe this violation, since only a small fraction of flows could be analyzed with Deborah integration, even below utilizations of 1. Some of the Deborah integration delay bounds are better than SFA FIFO. This fraction tends to increase with higher utilization. However, on the other hand, we can observe that our LUDB-FF is almost always better than SFA FIFO. The answer is simple. LUDB-FF solves recursively tandems, so it sets several thetas over several servers, while SFA FIFO only has a local view that sets a theta per server in isolation. The state-of-the-art analysis for arbitrary multiplexing, called TMA, is however worse than SFA FIFO, which is not too surprising. First of all, SFA FIFO, although locally, makes use of the FIFO property, and second of all, it is a well-known fact from queuing theory itself that the difference between an arbitrary analysis and a FIFO1 increases with increasing utilization. Here are plots that depict the actual delay bounds. On top you can see TMA, in between is SFA FIFO, and the best one is LUDB-FF. It might be hard to see, but the data analysis revealed that there are a few rare cases where SFA FIFO beats the more complex one, LUDB-FF. This is left for future investigation. It is not a bug in our code, and by now we know why this is the case, and we are already working towards exploiting this for improved bounds. This plot also nicely illustrates again that the gap between TMA and LUDB-FF gets larger with higher utilization, but also that they increase by different factors, which can be seen by the large oscillations of the TMA curve. To conclude this talk, with LUDB-FF, we advanced the DNC analysis in networks of FIFO queuing systems. It is a combination of the arrival bounding framework that was initially developed for arbitrary multiplexing and the LUDB analysis. LUDB-FF outperforms alternative approaches to bound flow delays, namely SFA FIFO, Deborah integration, and the arbitrary multiplexing analysis TMA. Our evaluation shows that LUDB-FF almost always beats SFA FIFO by a margin of up to 75%. Thanks for your attention, and feel free to ask questions.
Thank you indeed. Do we have any question for Alexander? I have just more a question. I saw once an article of yours with predicting flow prolongation. Is it something similar or not to your contribution now?
Yeah, very good question. Yeah, it is a bit similar, but also not. Flow prolongation, there you actually change the path of a flow. So for example, if one flow only goes through one server, flow prolongation means it will prolong that flow maybe to also the second server or the third server, and will basically throw out all combinations. That might seem a bit pessimistic, because then the flow will go through more servers, but because of the nature of the network calculus analysis, that can actually benefit the bounds, this flow prolongation. So, but here in this paper, we do not yeah, we do not change the path of the flows. We leave the path of the flows as it is.
Thank you. Thank you. I see.
Thank you.
Further questions, please? If not, thank you again for this very interesting contribution, and we may pass to the second presentation. And there are two authors, Mariam Akbari Moghadam and Douglas Down. Both are from McMaster University, Department of Computing and Software at Hamilton, Ontario. And the title is SEH, a size estimate hedging for a single server queue. I guess it's Miriam who is presenting, so the floor is yours. Thank you.
Hi everyone, my name is Mariam Akbari Moghadam. I'm a master's student at McMaster University. Today I'm going to talk about SEH, size estimate hedging for single server queues. The problem of scheduling of jobs in single server queues where preemption is allowed and processing times are known to the scheduler has been studied many times in the literature. The shortest remaining processing time, or SRPT policy, is optimal in the sense that it minimizes the number of jobs in the system at each point in time, regardless of the processing time distribution, and by doing so, it minimizes the mean sojourn time in the system, which is the expected amount of time that a job needs to wait in the system before being completed. However, SRPT is rarely deployed in practical settings because the assumption of knowing the exact job processing times prior to scheduling is not always practical to make. In these situations, job processing time estimates can be used. The shortest estimated remaining processing time, or SERPT policy, schedules jobs based on their estimated remaining times. However, it is too aggressive and has poor performance when the job processing times have high variance and large jobs are underestimated. For example, consider a case where a job with a processing time of 1000 enters the system and it's underestimated by 10%. So its estimated processing time is 900. The moment this job is processed for 900 units, the server assumes that this job's estimated remaining processing time is 0. So this job will block the jobs already in the queue as well as any new arrivals until it completes. In these cases, a policy that hedges against errors is needed. The shortest estimated processing time, or SEPT policy, is a version of the shortest processing time policy, and its difference with the SERPT policy is that it skips updating the estimated remaining processing times. This policy prioritizes jobs based only on their estimated processing times, and studies show that it has an impressive performance in the presence of estimated job processing times. It's also easier to implement than SERPT. The Guinness Index policy is a dynamic priority-based policy, and it's optimal in minimizing the MST in an MG1 queue. In the presence of job processing time estimates, this policy utilizes information about job estimated processing time and the job processing time and estimation error distributions to decide which job should be processed next. We have the following model. We have an MG1 queue. We allow preemption, and our goal is to minimize the MST in the system. We have the following assumptions. We assume that the job's processing time is not known upon arrival, and an estimated processing time is provided to the scheduler. We assume a multiplicative error model because studies show that it's a better reflection of reality, and it results in having an absolute error proportional to the job processing time. We also assume that the error distribution is independent of the job processing time distribution. The estimated processing time of a job is calculated by multiplying the job processing time by the job processing time estimation error, and it's shown by S hat. The Guinness Index approach is an appropriate technique for determining scheduling policies when the job processing time and estimation error distributions are known. For a waiting job I, this index is calculated and it's shown by G of A sub I, where A sub I is the elapsed processing time. And at each time epoch, the Guinness Index policy processes the job with the highest index among all of the present waiting jobs. However, this index is very difficult to calculate and it may introduce significant computational overhead. Also, the assumption of knowing job size and estimation error distributions before scheduling might not always be practical to make, and scheduling speed is important in real environments. So our work is motivated by the form of the Guinness Index policy. From now on, whenever we refer to the Guinness Index policy, we assume that we only know the estimation error distribution and nothing about the job processing time distribution. We now introduce size estimate hedging, which is a simple dynamic priority scheduling policy. We would like to construct a simple heuristic by examining the form of optimal policies, and SDH is motivated by the notion of defining a policy in terms of an index. It combines the relative merits of two scheduling policies, SERPT and SEPT. Our motivation is that when a job first arrives at the system, we really have no basis on which to assume that the estimated processing time is incorrect. However, when the elapsed processing time of the job reaches its estimated processing time, we know for sure that the job's processing time has been underestimated. Studies also show that SEPT performs well when dealing with estimated processing times and in the presence of estimation errors, in particular severe underestimations. So we would like to combine these two policies. We are introducing a Giddens-like score function where a higher score indicates a higher priority. We would like to be aggressive and use SERPT until the point that we know a job is underestimated, and at that point we freeze the score, but instead of switching to SEPT, we give credit for the job's cumulative elapsed processing times. This way, any underestimated small job can still receive a high score and be processed, while underestimated large jobs will have a much lower score and do not interfere, even with underestimated small jobs. Furthermore, since we do not need to know the estimation error distribution, we do not have much overhead, and scheduling the jobs at a speed comparable to the SEPT policy is done. The score function of SDH is shown in this slide, where the scheduling decisions are only made at arrivals and departures. This slide shows the score function of the Guinness Index policy and SDH for a job with an estimated size of 20. We can see that under both of these policies, the score is increasing, and the moment the job reaches its estimated processing time, the slope of the score decreases. However, this slope is more severe for SDH, but our numerical results show that the performance of these two policies are really close. We evaluate SERPT, SEPT, SDH, and Guinness Index policy in our simulations. These policies all fit into the scoring framework and assign scores to each job and process the jobs in the queue in the descending order of their scores. We allow preemption, and a newly arrived job can preempt the current job if it has a higher score. The performance metrics that we consider are the mean sojourn time and mean slowdown, which examines the ratio of the sojourn time to the processing time. we consider the following simulation parameters. The first one is the number of jobs. We assume that whenever the first 10,000 jobs that arrive at the system depart, a simulation run ends. We also have K, which is the parameter for the job processing time variance. Sigma is the job estimation error variance, and rho is the system's load. We also vary K, sigma, and rho to examine different scenarios. We run sufficient simulation runs to reach a reasonable confidence interval. This slide shows the impact of the job processing time variance on the mean sojourn time. On the y-axis, we can see the MSD over the MSD of SRPT, which considers that the exact job processing times are known. We can see that for lower values of K, which indicate a high variance in job processing time distribution, SERPT's performance is very poor, but the Giddens index and SDH policy has a very close performance, and their value is really close as to if the exact processing times were known. Whenever the value of K gets higher, the gap between the Giddens index policy and SDH a little increases. And we can see that the Giddens index policy performs best over all values of K, and SDH has a desirable performance and really close to Giddens index policy. This slide shows the impact of sigma on the mean slowdown. We can see that as long as the estimation error variance is reasonable, the results are consistent for all of the policies. However, for higher values of sigma, which indicate high variance in the estimation error distribution, we can the job size estimates can be really wrong, and in these situations it's better to use policies that ignore the job size estimates completely, such as the LAS policy. And as you can see, under sigma equals to 2, LAS, or least attained service policy, that gives priority to the job with the least attained service, performs best compared to all to the other policies. However, we can see that EPT, SDH, and Giddens index policy have really close performance under all values of sigma. This slide shows the impact of systems load on the mean sojourn time, divided by 3 kinds of classes. The first one is on the top is for all of the jobs, and the next 2 is only for overestimated jobs and only for underestimated jobs. For all of the jobs, we can see that the Giddens index policy performs best, and SDH is next, and it performs very close to the Giddens index policy, especially for values for load values under 0.9, and SDH shows desirable performance for all classes of jobs, both for overestimated jobs and for underestimated jobs. This slide shows the impact of the job processing time variance on the mean slowdown. We note that we have included SRPT only as the baseline policy. If SRPT is not optimal for mean slowdown, it's just included for comparison. We can see that the SDH policy performs best in minimizing the mean slowdown of the system compared to Giddens index and SEPT policies. SERPT policy is not included for mean slowdown because for lower values of K, which is K that is less than 0.5, it's several order of magnitudes higher than the other policies. Also, we can see that for high variance job processing time distributions, for example, 0.25, the mean slowdown is really close to 1. And this distributions is distributions that are seen more in practical settings. So it means that most of the jobs are not affected and not slowed down by other jobs. We also evaluate the performance of the policies for a real-world workload, which is a Facebook Hadoop workload from 2010. This slide shows the mean sojourn time over the mean sojourn time of SRPT and varying sigma. We can see that the results is consistent with what we showed for the synthetic workload. And SDH and Giddens index policy perform best for all values of sigma. This slide shows the mean slowdown of the Facebook Hadoop workload under varying sigma. We can see that for lower values of sigma, which indicate low variance in the estimation error distribution, SDH is performing best among all of the policies. In conclusion, SDH is easy to implement. It performs close to the Giddens index policy and generally outperforms SDRPT. The Giddens index and SDH policies outperform SDPT with lower variance in estimation errors and have an MSD near the optimal MSD obtained without any estimation errors. SDH also performs best across all values of job processing time variance in terms of minimizing the mean slowdown. In future, we would like to examine the SDH policy under other error models and also analyze the analytic bounds as how far SDH is from optimal. We would also like to examine how well policy is designed for worst case performance, like when the estimates have large variance, would perform with respect to the performance metrics considered in this talk. Thank you for your time.
Okay, thank you. Thank you again. Any questions for this contribution?
I have one question. Hi, Mariam. Thanks for the presentation. It was very interesting. I'm wondering if you considered looking at policies that don't necessarily need estimates of the remaining processing time, like tags or feedback queuing. I've seen you citing some of the work of Sharsh, and he's been analyzing the MG1 queue with feedback queuing. And those policies are known to deliver like close to optimal results. So similarly to shortest remaining processing time.
We don't hear.
We don't hear you, Mariam. Maybe now?
Yes, now. No.
Still not.
Still not.
Maybe we can use the chat then. And I see there is another question in the QA form from Andrea.
Yes, please.
Okay, cool. And follow-up question is, I saw you using the Facebook Hadoop workload. That is a workload that it's taken from like a MapReduce clusters with like parallel jobs. So I'm wondering whether the analysis that you did on the MG1 queue of these policies, whether that holds for like a framework like Hadoop, or there will be differences between those policies that are not captured by the simulated results. Yeah.
Hello, can you hear me? It's Doug Down talking.
Yes.
We hear.
I'm the co-author, and given her mic doesn't seem to be working, maybe I can try to answer the questions.
Cool.
So in terms of that workload, I mean, basically we use the workload in terms of the the trace in terms of the job sizes and plug them into the MG1 queue. So there's no parallel processing going on here. And if there were parallel processing, I think that there are some kind of initial results out there that if you look at systems with parallel processing with job estimates, actually the problems of, say, underestimated jobs become far less severe, because what happens is, essentially you end up only impacting one server when you kind of, if something goes wrong in terms of misestimating a job. So, I think there's some interesting questions in the parallel setting that probably the impact of misestimating jobs isn't as big a problem if you're looking in that parallel setting.
Cool. Yeah, I'm interested in these policies because these parallel frameworks like MapReduce, Spark, they are still using like very trivial policies. So I'm looking for things for more advanced policies that can improve the performance of the scheduling there. That's yeah. Thanks for the answer.
Okay.
There's one more question from Andrea on the Q&A in case you missed it.
Somehow I can't. Click on.
I can read it. Do you think it is possible to have an analytical study of SEH policy by resorting to the SOAP framework, for instance?
Yeah, so that's something we haven't done, and we actually had a chat with one of the people involved with that. And given that our policy can be represented by an index policy, we think that would fit right into that SOAP framework. So it's I think it's a probably fairly straightforward next step to get a little more in terms of analysis.
Okay, thank you. Just a small question of mine, just to learn something or understand better. We are speaking about MG1 priority queue. How the assumption of Poisson traffic is here important, because then it is a simulation study. Just thinking about analytical model with non-Poisson arrivals.
So I think qualitatively it doesn't. So in terms of doing simulation studies, qualitatively, I don't think it makes too much difference. I mean, I guess that there can be you know, maybe some of these problems are exacerbated if the arrival process is bursty. So if I kind of have that burstiness, it could be the case that if you know, in some of the policies where the performance is bad, if I have an underestimated job and there's bursty arrivals, then you know, the combination of those two things might make things worse. But qualitatively, I think you're going to have the same kind of behavior independent of what the arrival process looks like.
I see. Thank you. If there's no more questions, thank you again for the discussion, for the presentation, and we may pass to the last presentation. I guess it's Bogdan who is presenting. There are two authors, Bogdan Git and Aser Tantawi. And the title is An Approximate Bribe Queuing Model for Bid Advising in Cloud Spot Markets. Bogdan is from Databricks Amsterdam, and Aser Tantawi is from IBM Watson Research Center, Yorktown Heights. So please, the floor is yours.
Hello everyone, my name is Bogdan, and in this talk I'm going to present the analysis of a bribe queuing model, which can be used to set performance expectations in cloud spot markets. This is joint work with Aser Tantawi. Let me first introduce myself. I'm a software engineer at Databricks, where I'm tech leading a team that has the mission of making business intelligence tools like Tableau and Power BI perform well on our data analytics ecosystem. Prior to joining Databricks, I completed my PhD at TU Delft in the Netherlands. And during my PhD, I was a research intern at IBM TJ Watson. There I met Aser, who was my mentor and with whom I collaborated on the work I'm going to present next. It is widely known that most cloud providers expanded their resource offerings, not only in configuration, memory, CPU, storage allocation, but also in the type of SLA the users can expect. Paying a flat rate of the on-demand price results in rapid allocation and high reliability. However, providers may also offer spot instances for which users place bids, and which are allocated only when those bids exceed the spot price. The spot price is naturally decided by the provider. When users opt in for such instances, they may face delayed allocation and even worse, degraded performance due to interruptions. Amazon was the first cloud provider to introduce spot instances, but later on, also Google and Azure started offering equivalent resources. The cost benefits of using spot instances is known to be significant. Such instances can be allocated at discounted rates which are a small fraction of the on-demand price. However, as it turns out from our analysis of historical spot market prices from AWS, they are also quite prone to revocation by the cloud provider. It is not uncommon that AWS spot instances experience interruption rates that are higher than 20%. This is valid irrespective of the instance type or the region in which the instances are allocated, as it can be seen from the heat map depicted on this slide. Since MapReduce was first introduced almost 2 decades ago, there's been a lot of work trying to make these applications run in all sorts of environments, from homogeneous clusters to heterogeneous clouds to GPUs. However, most users are still reluctant to running their MapReduce or the more modern Spark applications on spot markets. The reason is that such applications are organized internally as workflows with multiple interdependent stages. In this model, the downstream stages require data transfers from upstream stages in order to continue the computation. Because of these data dependencies among internal stages, running on preemptible resources is particularly challenging because it may slow down significantly the application as it needs to recompute work that was already done and lost due to revocations. Two main research directions emerged with the spread of spot instances: bidding strategies to minimize preemption risk within a budget, and checkpointing policies for reducing the amount of recomputations. Our goal is orthogonal to these efforts. We seek to determine a relationship between the job slowdown and the bid value in order to help users set an expectation of the performance that may attain given their bids. Data analytics applications are elastic by design, which means that they can rapidly scale on a growing number of resources, while also tolerating failures when the allocation shrinks. Therefore, when the spot market revokes instances to accommodate users that place higher bids for their containers, for their resources, we requeue the preempted instances instead of kicking them out. In this way, the user keeps a glimmer of hope that at some point it will receive again the requested quota, assuming the spot price will drop. Nevertheless, the application will continue to make progress with a degraded performance, even if some of the containers are lost during runtime. The queuing system we use to represent our spot market running data analytics applications is the following. We consider a multi-server queue, which consists of a set of containers encapsulating a certain number of CPUs or cores that are allocated across multiple VMs. Jobs arrive to this queue having set a requested quota as a number of containers and a bit value that is associated with those containers. Requested containers are, for a given application, are scheduled independently from each other, which means that the system doesn't guarantee that all containers get allocated simultaneously. In this way, we take advantage of the application elasticity. This means that an application or a job may start as soon as a single container gets allocated without waiting for the remaining ones. But at the same time, when the application is running and is losing some of the containers that are allocated, the application can continue to make progress with degraded performance as long as there's at least one container allocated. Jobs have a total amount of processing which is split across multiple tasks that can be executed inside those allocated containers. Last but not least, the queue orders the incoming jobs and their containers by the bid values, with preempted containers being placed again in the queue in the appropriate position based on the bids. In the simple case of an MM1 queue, this queuing system, we can see that this queuing system degenerates into a bribing queue, which has an appealing job slowdown expression that was originally obtained by Kleinrock quite a few decades ago. In this expression, we denote the cumulative distribution function of the bit values by B of x, the server utilization by rho, and the job slowdown by S of x. However, we seek an approximate expression for our generalized model. And to do so, we have to introduce a parameter vector theta, which consists of two model parameters, theta0 and theta1, that act as scale and shape parameters respectively. First, theta0 acts as a replacement for the server utilization rho, which may not be available to an external observer. And second, theta1 captures a variation in the expression due to the model features that we have described previously. Hence, we have extended the expression that was originally derived by Kleinrock and wrote a close from approximate expression of the job slowdown as a function of B, the bit distribution, theta, the parameter vector, in addition to x, the bit value. In order to use the parameterized expression and provide bit advice at runtime, we need a dynamic estimator for these model parameters. To this end, we separate the estimation process into two independent processes, one for estimating the bidding parameters and the other for estimating the model parameters, in particular the theta vector. We use the sequence of bit values that are submitted to the system in order to derive the bit distribution. And we do so by approximating it with a beta distribution with parameters alpha and beta. Secondly, we use the approximated bit distribution from the previous step, and together with the observed values of the job slowdown, which can be obtained as jobs complete and leave the system, we employ an extended Kalman filter to estimate the theta model parameters dynamically. Both estimates of the bit distribution and the parameter values can now be plugged in into the job slowdown expression that we have derived and used for prediction. In this way, we can answer different types of queries that the user may ask our system. On one hand, we can determine for a given bit value that the user wants to place, what would be the expected level of service that the user can attain, but also vice versa, like for a desired level of service, what should be the user bit be. We validate this approach by means of simulation. So we have built a simulator that emulates the behavior of the system that we described previously. We create a workload consisting of jobs with service times that are sampled from a gamma distribution with mean 1 second. And we assume that these jobs arrive at a rate of 3.2 jobs per second with an imposed load of 80%. The simulated capacity has a total of 12 slots, and each job is requesting uniformly between 1 and 5 slots. We use 3 different bit distribution functions, linearly decreasing, uniform, and linearly increasing. The bit distribution is approximated by the beta distribution, and based on the method of moments, we can estimate alpha and beta from the average and variance of the observed bit values. We observe that parameters fluctuate quite closely around their values, which are governed by a ratio between alpha and beta being equal to 0.5, 1, and 2. Next, we show the evolution of the model parameters theta over time for the 3-bit distributions. We observe that theta 1 has an interesting catalyzing effect that drops to lower values whenever theta 0 is overestimated. So theta 1 is actually adjusting the prediction model to keep it accurate. It is also interesting to point out here that having just a single model parameters would not have been enough, because we would have missed the catalyzing effect of theta 1. And so which we wouldn't have been able to adjust the prediction model in case theta 0 is overestimated. Finally, we show the average job slowdown as predicted by our model versus the actual simulated value for the entire range of bit values. We find that irrespective of the shape of the bit distribution, our model is robust and delivers high accuracy predictions, which is exactly what we wanted. To sum up, we presented a bribing queue that can be used to model the cloud spot market, which from which we derived the concise job slowdown expression as a function of bid. However, due to the complexity of the multi-work or multi-server setting, our expression is only approximate, and so we incorporated model parameters. We presented to make it practical and usable at runtime by users. We presented a method for dynamically estimating the bit distribution and the theta model parameters. We validated the resulting approach and the accuracy of our prediction using large-scale simulations. Thank you for your attention, and now I'd be happy to take any questions that you may have.
Yes. Yes. So congratulations for the results. Do we have any question? Not exactly. So
No questions.
once again, very convincing results. And thank you, and thanks for all speakers and all listeners. So if there's no other remark, we may close the session.
We do have a question so in your comparison, do you feed the model with the same traffic as the simulation? So in our model, we are moving from an MM1 queue to basically a multi-server, multi-worker queue. And we are feeding the model. The simulation that we create there, we are feeding the same traffic as in the multi-server, multi-worker queue.
Okay, thank you. I'm looking at the chat.
Yeah, so basically we want to move away from the MM1 queue, which it has the advantage that provides a very concise expression. But our main purpose with this is to turn it into a real-time spot advisor for customers. And in order to do that, there's no way that we can get that through analytical results. That's the analysis in our model. It's not tractable. So that's why we incorporated these model parameters to make it work with the traffic that we have used in simulation, which is actually close to like a real world workload. Yeah. Yeah, there are more details in the paper for sure, and yeah, we can take this offline as well.
I'm just wondering if for analytical models we could use GGM approximation by diffusion approximation, which is quite close and maybe furnish some new results.
Yeah, that would be interesting for a comparison to see whether that could provide yeah, more robust results for different types of workloads. So that's a good suggestion.
So thank you again.
Yeah, thanks as well.
And we close the session now. Yes, no other remarks. So thank you and bye.
Bye-bye.